Hi, everybody. Dr. White back here again with section 2.1. We're beginning our study of random variables. Chapters 2 and 3, heavily about random variables. Chapter 2 is what we call discrete random variables. Chapter 3, continuous random variables. Section 2.1 is our introduction to the concept of random variable in general and introduction to what it is to be a discrete random variable. So random variables are things that are associated with chance process, and they're all about probability. Informally, you could think of a random variable as a number whose value depends on the outcome of a random experiment. A more mathematical definition would be here. Let's let S be the sample space for some random experiment. A random variable is a function that we're going to write capital X. We'll often write random variables capital letters. A random variable is a function, capital X, that assigns a unique real number, little x, to every outcome S in the sample space. And so mathematically, you would write x of S is x, meaning that when you get outcome S, then the number little x is what's assigned to it by the random variable. And that sounds pretty abstract, but you really met random variables a lot, and you've thought about them a lot without using that name. For example, suppose your random experiment is you flip a fair coin 3 times. Then let's let capital X be the number of heads you get. It's a random variable. Capital X is going to be a number, 0, 1, 2, or 3 heads, but which one depends on the outcome of that chance process, Random variable. Thinking about it more formally in terms of that mathematical definition, let's look at this table here. The first column that I've labeled little s is the set of all possible outcomes. It's the sample space, capital S. And so little s here stands for a particular outcome. And the second column labeled little x, well, what I'm doing here is saying what the little x would be for each particular outcome according to this random variable. And so if your outcome is t, well, the number of heads is 0, so the function assigns 0 to that outcome. And that function is going to assign 1 to each of the outcomes HTT, THT, and TTH. It assigns 2 to 3 other outcomes, and it assigns 3 to the HHH outcome. So that table there is showing you how the function capital S works, how the random variable capital S gets its numbers. Okay, some other concepts associated with random variables. Suppose that you have in mind a particular probability P on that sample space S. Now remember, a probability is a function from sets of outcomes from events to a number between 0 and 1 that represents the probability of that event. So if you got a particular probability in mind for that random experiment, you can construct what's called a probability mass function, or PMF for short, for your random variable capital X that's associated with that experiment. So for example, in the coin flipping random experiment where capital X is the number of heads you get, let's say you have in mind that equal likelihood probability where each of the 8 outcomes is equally likely. That's the fair coin probability model. Well, here, this table here is the construction of the probability mass function. Now, the probability mass function will be called little f of little x, where x is a possible value of the random variable and little f is your function. If you ever have more than one random variable floating around and you need to make sure everybody knows what you're talking about, you'll put the random variable as a subscript under the f. So like f sub capital X of little x. So how does it work? Well, the possible values for the random variable are down this first column, so I call them little x, okay? Each one of those is like a little x. And then here, these are all the probabilities that go with each of those possible values. Since there's only one of the 8 outcomes that goes with 0 heads, then f of 0 is an 8th. And by similar reasoning, f of 1 is going to have to be 3/8 because of the 3 outcomes that would give you a 1 on the random variable. And when you get 2 heads, there's 3 of those outcomes, and so 3/8 is the probability, and the probability of 3 heads is 1/8. So that little table here is a table of values for the probability mass function. Now, you'll notice in the book, they kind of slip into doing something that I don't really like, but they do it. They switch over from thinking of S as the set of all outcomes in the random experiment to thinking about S as the set of all possible values for the random variable. So like 0, 1, 2, 3, instead of those 8 different HTH type outcomes, right? So they'll do that. And they start talking that way as soon as they start telling you about general properties of a probability mass function. The first general property is that f of a possible number x is always bigger than 0 for all of the possible values x of the random variable. That certainly happened here. Those were all bigger than 0. Another thing you'll notice is that since something has to happen, the random variable has to assume one of its possible values. And so there's a 100% chance of getting something. So those numbers there ought to sum to 1. And you look at them, and sure enough, they do. They sum to 8/8, 1. That always happens for anything to be a probability mass function for a random variable. It has to have the f of x is sum to 1. The sum over all the x in the random variable sample space of f of x is 1. You can get probabilities for x to be in any particular subset by just adding up the f of x's for the x's that are in that subset. That's what this is saying right here. So like if A here stood for the event of getting 2 or more heads, then you're talking about the capital X being 2 or 3. And if you add up 3/8 and 2/8 right here, that would be the probability of 2 or more heads. That's what this property is saying here. So you can represent probability mass functions using a table of values, but you know that you can also represent functions using their graphs. There's 2 nice ways to graph probability mass function. One is through what the book calls a bar graph. I'd rather call it a stick graph, maybe, because these look like sticks rather than bars. You got little sticks over each of the possible values of the random variable. And the height of the stick is set to the f of that possible value. So like f of 0 is 1/8, we're 1/8 high. F of 1 is 3/8, we're 3/8 high, and so on. So a nice little kind of symmetric set of sticks, giving the probability mass function. You could also, instead of using sticks, use, I'm going to ignore that telephone. You can construct little rectangles. And each rectangle is centered over the possible value of the random variable. And each rectangle extends half a unit in each direction so that its base is 1. And its height is just the probability of getting that particular value for the random variable. So in that way, the areas of the rectangles stand for probabilities. The area of this rectangle right here is 1 unit wide times 1/8 high, 1/8. Okay, and that's the probability of getting 0 heads. This rectangle is, again, 1 unit high, 3/8, 1 unit wide, 3/8 high, 3/8 is the area. That's the probability of getting 1. The probability of like 2 or more heads would be the area of those 2 rectangles. You add them up, and it turns out to be the probability because of the way that the widths of the rectangle have been set up. So that's how a probability histogram for a discrete random variable works. Now, I want to point out what makes it a discrete random variable is that there is a smallest possible separation between 2 possible values. In this case, that smallest possible separation is 1 unit, like between 0 and 1, or 1 and 2, or 2 and 3. It doesn't have to be the case that the possible values are all whole numbers. That's happening in the example that we're looking at here. There just has to be a smallest possible separation to have a discrete random variable. Once you've got a discrete random variable, you can always make a table like this, or you could make one of these graphs to express the probability mass function. Next up is the cumulative distribution function for a random variable. It is simply defined to be capital F of x, where x is a possible value of the random variable. Capital F of x is the probability of the random variable turning out to be less than or equal to x. Okay. Now this function is actually defined for all real numbers x. Okay. And let's see what it is in the case of our coin flipping example, where capital X is the number of heads in 3 tosses of the fair coin. So what's f of x? Well, it turns out to be what we call a piecewise defined function. If little x is less than 0, then f of x is the probability of getting less than 0 heads, which is 0. Okay. On the other hand, what if little x is at least 0 but less than 1? Well, what would be the probability of less than or equal to little x heads? Like, say x were 0.3. Well, you could give 0 heads, and that would happen. If you got 1 head, then already the x is bigger than 0.3. So for any x in this range, the only way to get that to happen is to give 0 heads, and the chance of that is 1/8. In the same way, the only way, if x is in the range from 1 to anything less than 2, the only way to get that number of, the only way to get less than or equal to that number of heads is to get 1 head or 0 heads. And that would be 3/8 is the probability. And so on. And I'm sorry, there is an error there. This should say 6/8 here, and it should say 1 here. Why is that? If x is at least 2, then the way, but less than 3, then the way you get less than or equal to x heads would be to give 0, 1, or 2 heads. And the chances for that are 1/8, 3/8, 3/8. And that adds up to 7/8. So that should have been 7/8 there. If x is at least 3, then what's the chance of coming out less than or equal to x? Well, if you came out 0, 1, or 2, or 3 heads, you would be coming out less than or equal to the x, as long as the x has to be bigger than or equal to 3. But you have to get 0, 1, or 2, or 3 heads. The probability of that is 1. So that's a 1 right there. So the graph of capital F of x would look like this. It's at height 0 for all of the little x's that are less than 0. It's at height 1/8 for all of the little x's that go bigger than or equal to 0 and less than 1. So you notice there's a dark circle here to indicate that capital F of 0 is the 1/8, not the 0 down where there's that empty circle. And similarly, capital F of 1 is not an 1/8, it's up to 4/8. That was a 4/8, darn it, because it's a 0 and a 1/8 and a 3/8, so 4/8. Boy, I have to fix that. And then it stays flat again. The probability of getting less than or equal to x, if x is like any number in between here, like say if x is here at 1.5, the chance of less than or equal to 1.5 x's is 1.5 heads is the same as the chance of less than or equal to 1 heads. So it stays at 1/2. And then as soon as x gets up to 2, then the possibility of getting 2 heads is included in being less than or equal to x. And so we throw on another 3/8, we're up to the 7/8 level, okay? And then as soon as you hit the 3, then the capital F bumps up to the 1 level, because the probability of less than or equal to x heads would have to be the same as the probability of less than or equal to 3 heads. And you're going to stay at the 1 level forever. So there's the graph of the cumulative distribution function. So I want you to notice 4 things about it. First of all, it's what we call monotone non-decreasing. And that means if you read from left to right, the graph never falls. It may stay the same for a while, but it will never fall. That's monotone non-decreasing. It's also continuous from the right. And that means if you start from anywhere on the graph and you like head to the left to a particular point, okay, I'm sorry, I won't do the calculus definition here. Shall I? Yeah, I'll go ahead and do it. Say you're at the point, you're looking at the point 3, and you look at the limit of capital of f of x as x goes to 3 from the plus side. Well, that limit would be a 1. And it's the same as the value of f of 3, continuous from the right. It's not continuous from the left, because if you start with x a little bit less than 3, capital F of x is 7/8. As you move the x closer to 3 from the left-hand side, it stays at 7/8. So the limit of capital F of x as x goes to 3 from the left side is 7/8. But that's not the value of capital of capital F of x, capital F at 3. That value is a 1. This function is continuous from the left all the time. It's not continuous from the right all the time. And lastly, the limit as x goes to minus infinity, just let x go this way, that limit is 0. In fact, for this function, it becomes 0 and stays that way. Also, the limit as x goes to infinity is 1. In fact, this function became 1 and stayed that way. These 4 things happen not just for our example, but for all cumulative distribution functions you will ever meet. Okay, let's do some examples by way of exercises. This is number 3 in the exercises for section 2.1. So I'm going to read this out for you. For each of the following, and we're just going to do part C, for each of the following, determine the constant C so that f of x satisfies the conditions of being a probability mass function for a random variable x. And then they want you to make a bar graph of the probability mass function. So here's what they have in mind. They're showing you a function here, little f of x. And the rule for the function is that it's some number c times 1/4 raised to the power of x. And the domain is supposed to be all the whole numbers x bigger than or equal to 1. Okay? So that's the function they propose. And they say, all right, we don't know what c is, but this function is supposed to be the probability mass function for a random variable. From that, can you figure out what the c has to be? Okay? What does c have to be for f to be a probability mass function? Well, there's several things that probability mass functions have to do. They have to satisfy these 3 properties. And one of them is this property B here, that the sum of all of the f values over the whole sample space for the random variable has to be 1. So let's take that in mind. 1 has to be the sum over all possible values for little x of f of x. So that's the sum x goes from 1 to infinity of c times 1/4 to the x. Now, this is almost the official formulation for a geometric series you learned about in Calc 2, except that they would be summing x goes from 0 to infinity of a fixed number times another fixed number raised to the x power. Okay? Like this would be formally the whole geometric series. But that includes an extra term, the term where x is 0. Now, when x is 0, this would be c times 1/4 to the 0, c times 1, c. And so when you write this down, you're actually writing down an extra c. So I'm subtracting off a c here in order for this equal sign here to really be true. Okay? Now, this actually gives me the possibility for an equation that I could solve for c. Because when I stare at this, I realize, oh yeah, it's a convergent geometric series, and I got a formula for what it converges to. It's the little constant factor divided by 1 minus that ratio amount, 1/4. So this works out to c over 1 minus a fourth minus a c. So 1 is equal to it. That's an equation we could solve for c. And here I begin to do that. I factor c out on the right-hand side. And then I compute these numbers. 1 minus a fourth here on the bottom is 3/4. 1 over 3/4 would be 4/3. So did that work here? Now 4/3 minus a 1 is 4/3 minus 3/3, which is going to be 1/3. So 1 is a third times c. Multiply both sides by 3, and I get that c is 3. Okay? So now I know exactly what the probability mass function is. It's a 3 there, times 1/4 to the x. So I can make my bar graph. I just put my possible values on the x-axis here, and then I put 3 times 1/4 to the 1, 3 times 1/4 to the 2 power, 3 times 1/4 to the 3, which works out to 3/64. And there's rectangles over all of these other values. They're just very, very short, so I'm not going to go ahead and write them all in. So there's a totally decent discrete random variable that happens to have infinitely many possible values. Here's exercise 7. Let's say you got 2 dice, and you just roll them, and the rolls are independent. How one comes out has no effect on how the other one might come out. And let's construct a random variable. Let's let x be the minimum value of the 2 rolls. It's a totally decent number that depends on the outcome of the chance process. It's a totally valid random variable. Let's see if we can figure out a probability mass function for it. So to do that, I'm going to start with the sample space for the random experiment itself. I'm going to start with a construction of the random variable x itself. I've got to tell you for every item in the sample space what number it pops up with. And the best way for me to do that is to construct a table where this column tells you how die 1 came out, and this column tells you how die 2 came out. And so there's 36, different things could happen. Like if they both come out 1, the minimum value of the 2 is 1. If die 1 came out 1 and die 2 came out 2, then the minimum value is still 1. And so on for all the other entries in this table. Okay? Now, let's see if we can get the probability mass function for capital X out of this. I first need to write down the possible values in a column. So that's the one I label little x. And the minimum could be anywhere from 1 to 6. And the next one that I call little f of x is the probabilities for getting each of those. I'm in an equal likelihood situation here because it's fair dice. So each of these 36 outcomes is equally likely. So all I got to do to find the probability that the minimum is 1 is to just count up how many times the random variable showed me a 1, and that turns out to be 11 times. And similarly, counting for the other possibilities, I get these probabilities: 936, 736, 536, 336, and you can see there was only one case where the minimum was 6. So 1 out of 36 is that chance. And so Part B of the problem was to make a probability histogram for X. And so here I am trying to center my rectangles over each possible value and doing kind of a bad job right there. And also, I think that these values here kind of like aren't drawn very well to scale, but hey, I'm trying. Here's my last exercise. So number 11, they say we got a random variable and we're going to give you its probability mass function. The domain is x equals 0, 1, 2, and so on. So those are the possible values of the random variable. By the way, the possible values of the random variable are called the support of the random variable. Okay. What's the probability at each possible value? It's 1 over x plus 1 times x plus 2, which, by the way, if you use like the partial fractions technique from Calc 2, that we use as a trick to integrate certain types of functions, you could actually break this up as the difference of these two fractions. So they want you to find the probability that x is bigger than or equal to 4, given that it's bigger than or equal to 1. Let me go ahead and first see if I can get a formula for x to be bigger than or equal to m for any number m. So that would be the sum, x goes from m to infinity, of f of x. I'm writing on this property of probability mass functions, this third one here. Find the chance of an event, sum up the values of f of x that go with the event. Okay, now it's going to be a lot easier for me actually to sum this difference rather than the more complex fraction. And you'll see why down here. So when x is m, my quantity is 1 over m plus 1 minus 1 over m plus 2. When x is m plus 1, it's 1 over m plus 2 minus 1 over m plus 3. The next one that would have been here is 1 over m plus 3 minus 1 over m plus 4, and it keeps going that way. And you can see there's going to be some cancellation. The last term cancels the first term of the next one, forever and ever and ever. And so the result should just be, what we call one of those telescoping sums from Calc 2. The result is just going to be the first term in the first member. It's the 1 over m plus 1. That's the chance that x is at least m. So back to the conditional probability. By definition, that's the probability of this intersection over the probability that x is at least 1. Now, if I'm at least 4 and at least 1, I have to be at least 4. And if I'm at least 4, I have to be at least 4 and at least 1. So this event here is really the same as this event here. Much simpler event. And then I apply my formula and I get 1 over 4 plus 1, 1/5, and 1 over 1 plus 1, 1/2, and that works out to 2/5. So that's all the examples I had in mind. Sorry that this was so messed up. No, I'm sorry, not this, but cumulative. This was so messed up where it should have been a 4/8 here and a 7/8 here and a 1 here. I just slipped from writing down cumulative distribution functions to probability mass function stuff. Yeah. Other than that, good day, and I'll see you later.